This is Kate at the Library of Whispers, and today we're going to do a bit of vintage reading about Earth and the solar system from this lovely Time Life book. It's called Frontiers of Time, and it's from a series called Voyage Through the Universe. Now this book physicists. If the universe contains enough matter, a proposition neither confirmed nor denied so far by observations, one day in the remote future its expansion will slow to a stop. Then, in a reversal of the Big Bang known as the Big Crunch, the cosmos will begin to contract until it finally collapses to a point of infinite density. Because physics cannot describe such a state, what happens next is pure conjecture. But a few daring cosmologists, spiritual heirs to the first myth-makers, imagine that just as Brahma opens his eyes each day on a whole new universe, the process could commence all over again with a new Big Bang, and the cycle could repeat forever. Perhaps most difficult to grasp in these strange tales of beginnings and endings are the huge stretches of time involved. Galaxies, for example. Will take not a billion or a billion billion, but a billion 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 years to die. If the universe never stops expanding, interactions between certain subatomic particles may still be occurring at a time equal to a galaxy's duration, repeated a billion 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 times, then a billion 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 times more, then a billion 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 times more than that. The basic chronological unit in such scenarios is itself incomprehensible in human terms. A billion years ago, the only creatures existing on Earth were one-celled organisms, and much of evolution's rich tapestry of life was yet to unfold. A billion years hence, Earth will have altered completely, wrought anew by continuously shifting continents, recurrent ice ages, and occasional cosmic bombardments by asteroids and comets. Against such an endless backdrop, the entire 5,000-year history of civilization has been no more lasting than the flash of a lightning bug. Earth in flux. During its brief movement under the sun, humanity has received a misleading impression of the planet, its mountains and oceans seeming like permanent aspects of an essentially stable countenance. In reality, the only constants as time progresses are cycles of incessant change. Nowhere is this more apparent than in an examination of Earth's future, informed by analysis of its past. Actually, investigators of the geologic record have been relatively slow to recognise just how mutable Earth is. Geologists have known since the middle 1800s that the ice ages play a crucial role in sculpting the landscape, but not until the 1960s did they wholeheartedly accept the notion that the continents themselves are variable features of Earth's surface, drifting across the globe to smash together and then rip apart again in a kind of slow motion demolition derby that shows no signs of letting up. Earth's surface consists of about 10 so-called tectonic plates on which the continental land masses rest. As these plates slide over the partially molten layer below, they separate along mid-oceanic ridges clues to ancient magnetism locked in the geologic record. Researchers have been able to trace plate movements back nearly 600 million years. About 514 million years ago, for example, not long after the first shelled creatures appeared, according to the fossil record, the expanse of rock that would later be named North America lay along the This is known as subduction zones. The edge of one plate will slip under another and be dragged down into the interior, pulling the rest of the plate with it in a steady direction. Magnetic irregularity. Deeper below the surface, the rolling action within a fluid layer, known as the outer core, may lead to another form of instability in Earth's magnetic field. electricity through complex interactions among a thick layer of molten iron alloy known as the outer core. That's in orange here. A solid inner core, the yellow, and the planet's rotation. That electric current in turn generates a globe-girdling magnetic field. The action of this geodynamo creates field lines of force, often called magnetic flux, in a pattern reminiscent of the field lines from a simple bar magnet. On present-day Earth, the flux lines emerge into space from the southern hemisphere and re-enter the planet in the northern hemisphere, at the boundary between the outer core and less dense upper layer known as the mantle. The magnetic field mirrors the shifting patterns of convection in the molten outer core. As a result, patches of reverse flux, regions where some field lines are oriented opposite the lines surrounding them, occur sporadically in both hemispheres. In these pictures below, some scientists theorize that the gradual propagation and intensification of reverse flux patches may periodically trigger a planet-wide reversal of the magnetic field. So in these images here, the two maps above projected from measurements made at the surface in 1777 at the top and 1980 below show the directional orientation of Earth's magnetic field at the core mantle boundary. Patches of reverse flux inward, that's the blue sections, in predominantly outward, they're the red sections, regions, and vice versa, may be the result of upwellings in the fluid outer core, as shown here. Magnetic field lines associated with upwelling fluid in the orange diffuse up and down through the mantle in the brown, producing localized spots of outward or inward flux in opposition to the flux direction of the surrounding region. At the Redbird magnetosphere, preliminary signs of a magnetic field reversal include a marked decrease in field intensity measured in units known as nanoteslas. The strength of today's field, for instance, seems to be decreasing by about 7% each century. As the decline progresses, the stable dipolar arrangement begins to give way to more complex and weaker field structures. The illustration at left, for example, depicts one hypothesis for the advanced stages of such a transition, the so-called quadruple configuration. Not only is the quadruple magnetosphere less extensive than its dipolar counterpart, but shifting regions of reverse flux allow solar field lines to reconnect with terrestrial field lines at the equator, as well as at the poles. This increases access by solar particles to Earth's upper atmosphere, with potentially serious effects. During periods of heightened solar activity, such as the onset of violent solar flares, the Sun releases streams of highly energetic particles called solar cosmic rays that have been linked to the formation of nitrogen oxides. These in turn can cause partial destruction of the atmosphere's ozone layer, which normally prevents harmful ultraviolet rays from reaching the surface. With Earth's magnetic defences down, a few intense solar flares could substantially deplete The strikes occurred on land or soon eroded by wind and rain. Some are still visible, however. Shown here are 4 of about 120 impact sites around the world that bear witness to Earth's vulnerability to external forces. So let's have a look. In this image on the right we see, so this is in Australia. It's a circular configuration, nearly 22 kilometres across and about 142 million years old. Such formations of uplifted rocks typically occur at the centre of complex impact craters. And then below here, this picture, this is also in Australia. Less than 1.5 kilometres wide, Wolf Creek crater lies on the northern edge of Australia's Great Interior Desert. The crater is about 2 million years old. And then at the top, this is Manakougan crater in Quebec. Canada is heavily eroded. A 100-kilometre wide crater thought to be about 212 million years old. And then down below, another picture from Australia. 4 craters near Henbury Station, Australia, are part of a cluster of 12 in an area 1 kilometre square. The cavities were created some 4,000 years ago by fragments of a single meteoroid that broke up just before it hit the ground. The dating of impact craters on Earth suggests that bombardments occur about every 30 million years, a cycle that roughly corresponds with the Sun's periodic crossing of the mid-plane of the Milky Way as it orbits the galactic centre. One theory suggests that passage through the dense concentration of gas dust and stars in the mid-plane perturbs the orbits of comets believed to hover around the Sun in a vast and distant swarm known as the Oort cloud. Kicked out of their normal trajectories, the comets fall in a deadly rain on the inner solar system. Connections or coincidence. In recent years, scientists have looked at possible links between the Sun's movement through the galaxy and geophysical events and processes on Earth. For instance, as depicted in the series of galaxy images above, about once every 100 million years, the solar system crosses one of the Milky Way's spiral arms, regions about 1,500 light years wide that are dense with gas and dust. Some investigators theorising the passage through a dusty arm could change the amount of sunlight reaching Earth, point to a possible correlation with the occurrence of long ice epochs. Others liken the effects of this passage to those brought on by the Sun's crossing of the galactic plane. That is, a periodic hail of comets. Still others note that because spiral arms are the breeding ground of massive, short-lived stars that expire as violent supernovas, Earth would have more frequent encounters with the high-speed particles, cosmic rays, ejected by vast store of hydrogen is steadily transformed into helium. The duration of this process, known as the main sequence phase of stellar evolution, depends directly on mass. The more massive the star, the more rapidly it uses up its hydrogen, and the briefer its time on the main sequence. Stars with more than 10 times the Sun's mass are the most profligate spenders of hydrogen. In less than 500 million years, they move off the main sequence and very soon thereafter explode as supernova, blasting all into stellar space within a radius of about 300 light years. Luckily for Earth and its planetary siblings, the Sun is an average-sized star whose finale will be much less sudden. The end of the Sun's main sequence phase is still some 5 billion years away, and no supernova cataclysm lies in wait beyond that. As shown on the following pages, however, the denizens of the solar system can expect changes no less dramatic and no less fatal as the Sun negotiates the remaining stages of its long life. In a sense, the changes have been happening all along. The present-day Sun shines some 40% brighter than it did in its infancy. As the newborn star grew in power, its burgeoning heat baked tiny Mercury and transformed Venus into a noxious oven. Many eons hence, these bodies will have vanished into the ravening depths of a sun bloated and reddened beyond recognition, and the once fruitful Earth will be barren. But farther out, the moons of Jupiter and Saturn will be emerging for the first time from the primordial deep freeze. A few billion years after that, however, the Ice Age will return for good. Whatever is left of the solar system will circle its shrunken remains of the Sun